In this video we're going to discuss moving using electromagnetism, or electromechanics, so we're really getting into the heart of what this week is all about. If we take our current carrying wire, which is generating its own magnetic field, and place it in an external magnetic field, which is one we apply ourselves, these two magnetic fields will interact and our wire will experience a force causing it to move. So here's my current carrying wire, and it generates its own magnetic field and concentric rings around it, kind of like a tree trunk shape. We're going to then add this to an external magnetic field, and this could be just two poles of a magnet, which we then look at the force between. So a quick word on how we represent 3D fields in 2 dimensions. So this magnetic field is represented by a series of crosses, and this means that the field is going into the screen. If we could see into the screen and look at this sideways, we'd see the arrow going along. If we saw a dot, this would mean that the field was coming out of the screen towards us. So imagine if you had an arrow. If it was going away from you, you'd see the feathers looking like a cross, and if it was coming towards you, you'd see the pointy bit looking like a dot, or at least until you got out of the way. So what we're going to do is combine these two magnetic fields together, and this acts like superposition. So we'll have the fields reinforcing in some places and cancelling out in others. This gives us an overall field effect when we add them together, which means our wire experiences a force, shown by the green arrow, so it's actually going to move. If we set up our system so that the length of the wire runs at right angles to the magnetic field, we can find the force using the equation F is equal to BIL, or Bill if you want a nice way to remember it. So let's look at this and see what each term actually means. Well, first of all, here's our wire. F is the force in Newton, so as we saw, that was the direction the wire was going to move in, represented by the green arrow. B is the magnetic field strength of the applied field in Tesla, or T. Remember that the cross indicates the field travelling away, and a dot would indicate it coming towards you. Then we have I. This is the current passing through our wire in amps. Then we've got L. L is the length of wire which passes through the magnetic field in meters. It's worth remembering it's not the total length of the wire, but just the length of the wire that crosses over that magnetic field. The direction of the force, magnetic field and current are orthogonal. This means that they're all at right angles to each other for this equation to apply. So if we have our wire and our current I is in the Y direction, the magnetic field B is in the Z direction, so it's going into the screen, then the force the wire will experience, F, is in the X direction. So these are all at 90 degrees to each other. This is what our orthogonal term means. We can adapt the right-hand rule from before. So the right-hand rule was used to find the direction of the magnetic field around a current carrying wire. So what I want you to do is to put your thumb pointing in the direction of the current. Then put your fingers in the direction of the applied magnetic field. So this time, because the field is going into the screen, your fingers should be pointing towards the screen. This means your palm is pointing in the direction of the force. So if you just moved your palm in the direction it's already facing, it will give you that direction of the force. And I like to call this Leah's slap rule because it really helps me remember it.